Hello, in this video we're going to look at the pendulum, which is perhaps the king of oscillating objects. So while we're in the middle of oscillations, we might as well include an analysis of that. So here is our string with a mass on the end. So the mass is hanging down with a weight mg. There's a tension in the string, which is T. We'll say the length of the string is L. We've got an equilibrium position hanging down here, and we say that the pendulum is some angle theta off to the side. Now, you'll see a lot of people analysing this in a lot of different ways. So don't get too bogged down in the differences between all of the approaches for analysing the pendulum, because they all come down to the same approximation we can drop in at a different point throughout the analysis. And we'll come back to that a bit at the end. But say we've got some distance here, x, from the equilibrium position. But of course, the pendulum isn't moving along x. This is perpendicular to the vertical equilibrium position, but the length of the pendulum isn't changing. So it's actually swinging along a curved path rather than this straight path. So we've got a different line going on here. And sometimes, yeah, people or even they'll say there's a different restoring force on this. If you want to think of the mass moving along the path of x, so it's moving perpendicularly to this vertical equilibrium position, then the restoring force is going to be a component of the tension. But that doesn't really make any sense, because it's not moving along that path. What's moving it along the curved path is a component of the weight that's acting tangentially to the pendulum. So that's what I'm going to deal with here. So what have we actually got happening on this? This is still angle theta around here. So our tangential force on this is going to be mg sine theta. That is what is pulling our mass back towards the equilibrium position, this mg sine theta. But we can see, looking at the right angled triangle that we've got at the top here, that sine theta is x over L. So we've got that is equal to mg x over L. Now, this is, we can always use Newton's second law. So let's think of this in terms of F equals ma. So our acceleration, this is the force. So the acceleration that's happening tangentially must be the gx over L bit, because we've got the m sitting there. So we're saying that A is equal to gx over L. Now, everything I've done here has been in terms of magnitudes, because I haven't thought too much about directions yet, at all. So this x, though, I've been measuring off to the left. So that x is saying left is positive, but our force component is going off to the right. So I've been saying that here, force is positive to the right. So I need to take that into account with all of this. And we're now going to get a minus sign popping up here, because the force is going in the opposite direction to the measurement for x, the displacement. And then that will appear in here as well. Now, this is looking great, because we get to this point and we're thinking, brilliant, we've got acceleration is proportional to negative displacement. So we've got SHM, woohoo. We can do what we want with this and use all of our SHM analysis techniques that we've already worked out. And this is sort of true, but sort of isn't. So I'm going to put an asterisk next to this. We need to come back to this at the end to see something that's hidden in the weeds with an approximation there. But let's run with it for now and see where we end up, and then come back and look at that at the end. All right, so if we've got SHM, we can say the acceleration is minus omega squared x. So omega, therefore, omega squared is going to have to be g over L, based on what we've got up here, because there's our minus, there's our x, so the g over L must be the omega squared. We know from all of the analysis that we've done inside SHM and circular motion and all of this sort of thing, and how the SHM and the circular motion are linked to each other, that omega is 2 pi over t, is what I'm trying to get at on all of this. Omega is 2 pi over t. That's what we had from our circular motion. So radians per second. Remember, this is our angular velocity, radians per second. So if we've gone through one circuit of 2 pi in the period for one circuit, that is our constant angular velocity. If the thing is moving in this constant circular motion, which is associated with our SHM oscillation, and we showed this in a previous video. So that's all good. So we've got that t, therefore, is 2 pi over omega. So t is going to be 2 pi divided by omega, 2 pi the square root of L over G. So that is our period of oscillation of our pendulum. So this is period of oscillation. Now you'll notice with this that it is not dependent upon m or theta or x at the moment. It only depends upon the length of the pendulum and the acceleration due to gravity. So if we've got a whole load of pendulums set up in the same part of the world, so they've all got the same g, they've all got the same acceleration due to gravity, their oscillation period will depend entirely upon the length of the pendulum. So if you want something with a longer tick, you want to get a big, I don't know, grandfather clock with a 2-second tick in your hallway because you want to turn your house into a stately home, well, you need a long pendulum. If you've got a little clock going on the mantelpiece, you're going to struggle to get a 2-second tick out of that. You're probably going to have, say, a 1/2-second tick because you can't really get a longer pendulum sitting there on top of your fireplace at home. So period of oscillation is going to depend upon the length of the pendulum. Now, we do have to come back to this asterisk back here. Well, okay, SHM, and we have spotted it here, of acceleration is proportional to the negative of the displacement, but it's not quite. There's a little bit of a fudge that I've just snuck into this, that they're not measured in exactly the same direction. So x was measured horizontally off to the left. That was x. But the acceleration is measured slightly downwards because it's moving on this curved path rather than the straight path. So although they are in opposite directions, as in one's going to the left, the other one's going to the right, they're not diametrically opposed to each other. So there's a little bit of an approximation kicking around here. And this is the same approximation of, well, which one of these forces. What if we had just decided, you know what, we're just going to model this as the tension that's causing the restoring force on this. That's the same approximation that's sneaking in there. And it's saying that x and s are more or less the same. And so we're saying that x, which we've got as being, well, sine theta, we had as being x over L. And we're also saying that s, using our knowledge of circles and such like, is going to be L times theta. So if we want x and s to be pretty much the same thing, then we need L sine theta to be pretty much the same as L theta. So we'll make that a roughly equal to. So we're wanting sine theta and theta to be pretty much the same. So we're getting into a small angle approximation. So, and this is the main difference between all of the different analysis techniques that you'll see when people are deriving this formula for the period of oscillation of a pendulum. Is at what point do they put in this requirement that the angle is small, that sine theta and theta are more or less the same at small angle. And we've seen this previously with things, you know, what sort of leeway are you going to want? You know, how much are you willing to accept a 1% error in this, in which case, you know, you might get up to a, you know, 5 degrees, you might be able to push things up to say 8 degrees, because it's a pretty slow change when you're on small angle between, you know, sine theta and theta. So yeah, it's a tricky one, but at some point you have to bring in this approximation. And yeah, that's what I've done here by leaving it to the end and then just dropping it in as this difference of direction. But the important part really is this here, this idea for a simple pendulum. So again, simple pendulum, like simple harmonic motion, we've just got this one restoring force, and we can see that it just depends then on the length of the pendulum and nothing else.